Hello everyone. Today I will be talking about classical straightedge and compass construction. So before starting the talk, I'll say two things. First one is if I have any net issue, please give me 2 minutes. I will again join from another device. And regarding if you have any doubt, you can always type in the comment box. I will look at it and you can unmute yourself and always ask. So the whole part I have divided into 4 parts. So in the 0th step, I talk about the prerequisites and I explain what exactly the problem is. In the step 1, I develop the theory and defining some intrinsic mathematical objects. In the next step, I associate the theory with the actual problem. So the problems are of geometry, but the theory I am defining is the algebraic setup. So I show how the algebra is associated with the geometry, and then in the final step, we actually answer the questions. Okay, so this is about some classic. This is called classical straightedge and compass construction because there are some problems posed by the Greeks. So they asked some question long back in the Euclidean geometry era. So after that, mathematicians like Galois and all they developed concept like field and answered the questions. So let's see. The first slide is about two basic mathematical objects. So all of you know what a set is. A set is just a well-defined collection of objects, and what is a function? So let's say if we have two set, so a function is just an assignment from one set to the another. So what are the things we can use? Straightedge. So what is a straightedge? This is just a ruler or scale without mark. Using a straightedge, you can just draw straight lines. You don't know the measurements. That is the difference. And then you can use compass. Compass you all know. So you have a hinge, you can put it there and you can draw a circle of a given radius. So yeah, as you can see, these are my two things I can use. Now I will see what the problems are. Okay, before that, let us define something. I'm defining something called binary operation. So what is a binary operation? Let's say, okay, as I have written, a binary operation on a set S is a function from S cross S to S. So what is S cross S? This is the Cartesian product of two sets. So they are just order pairs where both the components from S only. So it takes two inputs from S and produces an element of S as an output. Okay, it will be clear if I give examples. So yeah, for example, addition on integers. If you add two integer, you will get an integer. So addition is a binary operation on integers. Similarly, multiplication on real numbers. If you take two real numbers, multiply them, you get another real number. So this is a binary operation. But subtraction on natural number is not a binary operation. Why? Because let's say you minus 2 from 1. So the result is not a natural number. So it is not a binary operation. The next thing. Yeah, now I am going to tell you what the problems are. What the classical Greek problems are. So there are three problems. First one is doubling the cube. The question is it possible to construct a cube with precisely twice the volume of the given cube? I give you a cube and tell you that let's say V is the volume of the cube. What you have to do using straightedge and compass, you have to draw another cube whose volume is 2V. What is the next problem? Trisecting an angle. Let's say I have given you some angle theta. What you have to do, you have to trisect that angle using straightedge and compass. And the third problem is squaring the circle. So this question is it possible to construct a square whose area is precisely the area of a given circle? I give you a circle and tell you A is the area of the circle. You have to construct a square whose area will be A. So these are three problems. And with that, my first part is over.
Archisman,
Yeah.
what does it mean for us to construct a cube with straight edge and a compass?
Okay, so the question is that basically you can think of the side length. If I give you length 1, you have to basically construct cube root of 2. This is just a fancy way to stating it. Nothing. I mean, yeah, the question makes sense. You cannot draw, how do you make a cube in 2D? How do you draw that? So it's basically given a length 1, you have to form cube root of 2. Once you form that, you can say, yeah, now I can construct the cube because you know how to draw 90 degrees, right? Does this answer your question?
Okay, so we are just calculating the cube roots.
Yeah, so if you know that the given length is 1, you basically have to construct cube root of 2. Once you construct cube root of 2, the volume will be 2 exactly, right?
Yeah.
Yeah, that's what it is. So it is just a fancy way to stating it. That's all. Thank you. So yeah, these are my problems I have defined and the prerequisites I have told. So far, I don't think there is any question. If there is any question, you may ask. Otherwise, I will go to the next slide. Okay, I will proceed. Yeah, so this is the mathematical object I want to define now. This is field. So I would like to give an example first so that the people who are seeing it for the first time and do not like these axiomatic approaches much, they can relate. So whenever I am defining something on a set F, you can think of this as real numbers or rational numbers. So I will say it in an abstract setup, but you can always think of this as a real or rational number. Okay, so what is my object? I have a set F with two binary operations. One is plus, another, I mean addition, another is multiplication. And it satisfies some very basic properties as I have written. First one is associativity of the addition. You can see here A plus B plus C should be A plus B plus C. What is my next property? The addition should be commutative. That if you add A plus B, that should be same as B plus A. The next property is there should be an additive identity and we call that 0. So if you add 0 with any number, it will give you the same number. Now there comes the fourth property where we want an additive inverse for all the elements. Given any A, you can always find a B such that A plus B is 0. For example, let's say if you take 5, you always have minus 5. So these are the properties of the addition, four properties. But there is also one more operation, that is multiplication. That also should satisfy some properties. We will see them one by one in the next slide. Okay, so multiplicative must be associative also. So if you multiply AB first then C, it should be A multiplied with BC. The second thing is multiplication should also be commutative. So AB and BA should be same. Third thing is multiplication should also have an identity, and that time we were denoting the additive identity, defining it to be 1 because 1 into anything is that number itself. And finally, we should have a multiplicative inverse as well. But multiplicative inverse will not exist for all the numbers because 0 doesn't have an inverse, you know. You don't have any number such that 0 into that is 1. So for all other number, you have some 1 by that number. And the final thing is distributivity. So if you have A into B plus C, that should be AB plus AC. So yeah, any question? I think there is some noise anyway. Yeah, so in last two slide, I defined what a field is. It is just a set with two operations, addition and multiplication, and with all these property. This is my intrinsic object. I will keep using this. Now I'll go to the next thing. Yeah, so here are the examples. Q. Q is the set of rational numbers. You can see if you add two rational, you get a rational. If you multiply two rational, you get one rational. And all other properties are being followed, like associativity, commutativity, and all. Similarly, R. R is the set of real numbers. This is also a field. And similarly, C. C is the set of complex numbers. But N and Z are not fields. Why so? Because N, I already showed that N, I mean, you cannot take the inverse in the multiplication. If you take 2, half doesn't belongs to N. So N cannot be a field. Similarly, Z cannot be a field. Now going to the next part, I have to define something more that is called field extension. Let F be a field. We say F to K is a field extension if K is a field and F is a subset of K. I mean, F is a field, K is also a field, but F is sitting inside K. Then we say F to K is a field extension. For example, again, Q to R is a field extension because we know R is a field, Q is a field, and Q is inside R. Similarly, R to C is also a field extension. Okay. Now I am going to define something called algebraic and transcendental elements. So the notation f of x denotes the set of all polynomials over the single variable x whose coefficients are from f. Okay, so let's say in place of f, take r. Let's say I am saying r of x. What does it mean? It means all the polynomials where the coefficients are from real, but the variable is x. For example, let's say x square plus 2x, or let's say pi x square plus ex minus 3. These kind of things I will denote it by f of x. Okay. Now I am going to define algebraic and transcendental elements. Let's say f to k via field extension. So an element alpha belongs to k, I mean alpha in the bigger field, is said to be algebraic over f if there exists a polynomial fx in f of x such that f of alpha is 0. Okay, so it may look very difficult, but when I will give example, it will be very clear. And if a number is not algebraic, we call that transcendental. So an element b belongs to k is said to be transcendental over f if it is not algebraic. So let us look at the example. Yeah. So q is my field. Let's say I have the extension q to r. So root 2 is a real number, but root 2 doesn't belong to q. But I am claiming that root 2 is algebraic over q. Why? Because consider the polynomial x square minus 2. First of all, observe that this is a polynomial in q of x. Why? Because the coefficient is 1 here and minus 2 here. So 1 and minus 2 are rationals. So this is a polynomial in q of x. And again, if you put root 2 here, so f of root 2 is 0. That means root 2 is an algebraic number over q. Similarly, I, so this is backslash iota in LaTeX, this gives this output, this is iota. Similarly, I is algebraic over q because of the polynomial x square plus 1. Because if you take x square plus 1 equal to 0, so I is a root of that. That means I is also algebraic over q. But pi, e, these are the numbers, these are transcendental. So there exists no such equation satisfied by pi and e. And also I pi is a transcendental over r. Okay, so till now what I have defined field, I have defined field extension and algebraic and transcendental elements. But now I will define algebraic extension. What's that? Let's say I have a field extension f to k. I call this to be algebraic extension if all the elements of k are algebraic over f. So previously I defined what it means to be one element to be algebraic, but now I am defining the whole extension will be algebraic if all the elements are algebraic over f. Okay, so let's say f to k be a field extension. Alpha is the element of k. Now try to understand this notation. Previously I defined f of x, but now I am defining f of alpha. So this is the smallest field containing f and alpha. So for example, let's say you have q, you have r. Now I tell you q root 2. That means that is a field which lies above q and also contain root 2. So clearly f to f alpha is a field extension. Yeah, for example, r of I equal to c. You start with the field r and put I there. Then you want to see what is the smallest field containing the whole field r and iota. So that should be c. Okay, by the way, this iota is the imaginary number such that I square equal to -1. I hope everyone knows that. Okay, this is the last slide of the first part, I hope. So this talks about degree of an algebraic element. Okay, so someone is asking to repeat the concept of algebraic extensions here. I will go back. Yeah, so I am saying, okay, I hope you remember the definition of algebraic number. So an element of k will be called algebraic number if it satisfies some polynomial equation over f, then we call it an algebraic number. And then we call this extension to be algebraic if all the elements of the k are algebraic over f. For example, if you go back one slide back, sorry. Yeah, so if you look here, so I gave an example from q to r. Root 2 was algebraic over q. But if you consider pi is not algebraic over Q. So the extension from Q to R is not an algebraic extension. But algebraic extension means in the bigger field, all the elements will be algebraic over the smallest field. I hope that should be clear. Yeah. Yeah. So the next thing is that degree of an algebraic element. Let f to k be a field extension, alpha belongs to k, and this is algebraic over f. So what do I mean by alpha is algebraic over f? So alpha should satisfy some f of alpha equal to 0. But it is not necessary that this small f should be unique. Alpha can satisfy a lot of polynomials. I will give example, it will be clear. So the degree of the minimal such polynomial f is called the degree of alpha over f. What do I mean by minimal? I will directly go to the example to make it clear. Yeah. Consider the field extension q2 q of cube root of 2. What is this notation again? So this means the smallest field containing rationals and cube root of 2. So I know cube root of 2 is algebraic over q. Why? Because I can take this polynomial x cube minus 2. Once I have x cube minus 2 is a polynomial in qx, cube root of 2 is a root. So cube root of 2 is algebraic over q. This is one polynomial satisfied by cube root of 2. But at the same time, x to the power 6 minus 4, this is another polynomial, let's say g. So again, you can say f of cube root of 2 is 0 and g of cube root of 2 is 0. So what should be my degree, 3 or 6? So that's where the minimality comes into the picture. I have to consider the minimal degree. Again, you can find some polynomial of degree 12 satisfied by cube root of 2, but all those we don't bother. We just consider the smallest degree. Yeah, because x cube minus 2 is the minimal polynomial satisfied by it. Again, the degree of the field extension f to f alpha is the smallest field containing f and alpha, is defined as the degree of alpha over f, and it is denoted by, this is just a notation, so we write f alpha index f. We call this the degree of the extension. I think, okay, now the final results. So let's say f to k be a field extension and alpha is the algebraic number over f. Then f to f of alpha, this will be algebraic extension. Again, if you know some field theory or if you are smart enough, you can prove this, but for this talk, I will skip the proof and I will use this result. If alpha is an algebraic extension, then f to f alpha must be a, sorry, if alpha is an algebraic number, then f to f alpha should be algebraic extension. This is one result, and the final result, let f to k be an algebraic field extension. Now in place of alpha, I have two numbers which are algebraic over f. So now try to understand what this says. This says f of alpha 1 comma alpha 2. That means the smallest field containing f, alpha 1 and alpha 2. So this is one field. And what does the right hand side says? Right hand side says consider the field f of alpha 1. This is one field. Then consider alpha 2. And so f of alpha 1 is a field and alpha 2. Now consider the smallest field containing them. So we are basically saying these two fields are equal. This again can be proved, but we will skip the proof because we need the result, nothing else. And then already I defined the meaning of degree. So here is a relation between the degree, and it is also very easy to understand. So I am saying, okay, yeah. So you have f first, then you are going to the field f of alpha 1, then you are going to f of alpha 1 to alpha 2. So this is also extension f to f of alpha 1 comma alpha 2. We are saying this whole degree is equal to this degree multiplied by this degree. I hope you can see my cursor. So f of alpha 1 comma alpha 2 indexed f, the whole degree, first one to third one, should be the degree of second one to third one multiplied by degree of first one to second. These are all my results in the first step. Now we will go to the applied part of it. I am done with the theory part. I will wait for 1 minute or 2 minutes. Ask me if there is any question, any doubt, anything I need to repeat. You may type it or unmute yourself. Then I will go to the next step. So
What did you say is the definition of the degree?
definition of the degree of a field extension, right?
Yeah.
Yeah. Okay, so firstly, the degree of an algebraic element. What do you mean by an algebraic element? You recall, right? Algebraic element is the element that satisfies some polynomial equation, right? So there can be a lot of polynomial. You consider the polynomial of minimal degree. That is the degree of that particular element, degree of alpha. Now, what I am doing, consider the extension f to f of alpha. In this extension, I have a degree of alpha. I call that the degree of the extension.
Okay.
In general, I am not defining the degree of extension for f to k. There is also definition, but I don't need it. I just want to define the degree of extension for f to f of alpha, and that is precisely the degree of alpha over a. Any more question? Okay. So if you have no question, just try to look at these two results. I will recall them later, but these are the things I am going to use. And after this, it will be easier. I think this is the hardest part of the talk.
Bhaiya, could you go back to the slide which showed the definition of this notation f of alpha?
Yeah. Okay, just a minute. Yeah. So f of alpha denotes the smallest field containing f and alpha. I will give you one example. I am sorry that I didn't include it here. Let's say I have Q, set of all rationals. That is a field, right? Then let's say I have root 2. So now what do I mean by Q of root 2? So this is basically the field which has Q in it and root 2 in it. And you can check, so this field are the collection of all the elements of the form a plus b root 2 by c plus d root 2. This kind of elements. Does that clear?
Yeah. Thank you, Bhaiya.
Yeah, thanks. Similarly, you can see that r of I equal to c, because you consider reals. You put I there, then see what is the smallest field containing r of I, and the answer is c. Okay, so I think that's all. Till even if you have any more doubt, you can type always. I will answer. I will go forward. Yeah. So now I will say something that is called constructible numbers. So you have understood constructible numbers as in something that I can construct using straightedge and compass. That is my whole purpose. So I'm saying one, we don't know what do we mean by one, because in the beginning I told that I don't have a scale or ruler, so I don't need the measurement. So first I have to fix something called one. I mean, in your measurement, fix that is one and call that some unit, 1 unit, let's say. Once we fix one, I am claiming that we can construct any natural number a. How? Yeah. So let's say this is my center, the 0 marked. Then I know what my 1 is. So what will you use? You will of course use compass, not the straight edge. So first you take this measurement, the one you know. Put your needle here and take the measurement to the right side again. So 1 plus 1, now you get 2. In this way, you can get 1, 2, 3, whatever natural number you want. So natural numbers are done. Once you get natural numbers, let's say you get natural numbers to the right side. You just need to make a convention. So in the left side, what you will get? Of course, you have understood this should be integers. Just negative of that. If this is 1, on the left side, if I take the arc, putting my needle here, I will get minus 1. And once I get minus 1, doing that a many times, I can get minus a. So in this way, I can form integers. Once I construct integers, what should be my goal next? Of course, the rational numbers. Okay, so here I am claiming that if I can construct a and b, I can also construct a plus b and a minus b, and that is again very easy. So let's say you know the measurement a, you put the needle here, take the measurement a. Again, you put the needle of the compass here, take the measurement b. Then you take the whole thing, this should be a plus b. Similarly, what do you do for a minus b? You take a to the right side, But from this point, you take b to the left side. Why left side? Because I need minus b. And my convention is right side positive, left side negative. So then from 0 to this left part will be a minus b. These things are pretty simple. But the problem will occur if I want the multiplication and division like ab and a by b. They won't come simply. You need something more. Yes, here I am claiming if we can construct A and B, we can also construct AB and A by B. How? This is the construction. First, I fixed a unit distance. Let's say this is my 1, AC. Using straightedge, you can join AC. Then again, you cut the A length. You know what the A is, you know B is. My goal is to form AB. So the distance AE is A. Now what I do, I don't know the concept of angle because I don't want to to any extent. I just get the B. It can be here also, it can be perpendicular, it can be of any side, but I just take B, not on the same line, some other line. Then I extend this and draw these parallel lines. And you can easily draw parallel lines using the compass. Maybe you will draw 60° here, 60° here. That is not too difficult. So I make this triangle. Once I make this triangle, these two are parallel. So I have two similar triangles. I hope everyone remembers from school what a similar triangle is. If you don't remember, please ask me, I will explain. So ABC is one triangle, ADE, this is another triangle, and the lengths of the AC is 1, AE is A, AB is B. So now you know, of course, AB by AC, AB by AC. This will be same as AD by AE because of the similar angles. So that means B by 1 will be this whole length AD by A, and that implies the length of AD will be AB. So I started with 1 A and B, but I eventually got AB in my segment AD. I hope that is clear because these are the things I am going to use. So if you have doubt, please ask now. Okay, now I have showed the AB part. The next I will show the A by B part. That is kind of similar. Yeah.
I have a doubt. So we
Yeah.
cannot take any angle, right? For the creating a parallel line, we cannot take any angle we need because 1 and B are fixed. So like
Sorry. Yes, I'm extremely sorry for that mistake. So you have to just join that. You cannot take any angle. Thank you. Yeah. So who was that? I couldn't understand, but anyone, thank you who said that. Yeah. So it's not that you have to form any angle. You have to just join 1 and B. I am sorry for the mistake. You have to join 1 and B, and then you have to extend this, and you have A. Now what you have to do, BC is fixed, you have to draw a line parallel to BC. So it's not 60°. You just measure this angle through compass and draw that here. Yeah. Sorry for that. I hope this is clear to everyone now. You join BC, measure the angle BCA and draw the same angle DEA, join it. Then your AD will be of the length AB. Okay, moving on. Similarly, now you have to form A by B. So there also what you do, you form 1 here, B here, and your A is here. So you just join this B and C. Once you join B and C, you know this angle ABC. Same angle, okay, sorry, not ABC. You know the angle BCA, the right side angle, the double marked. So what you do in this place E, you draw the same angle, join them. So these will be parallel. And if they are parallel, again you use the similar triangle wala thing. So your AD by AE will be AB by AC. So A by B will be AD by 1. That is the length of the segment AD will be A by B. I hope this is also clear. So far what have we shown? That given A and B, you can construct A plus B, A minus B, AB and A by B. So once you can do all these, I am claiming that the rational numbers are constructible. And also the set of all constructible numbers is a field. Why this is a field? I already proved it, that A plus B is there, AB is there. So A by B is there means inverse is also there. Thus you can prove C is a field. Okay, now I want to show the set of all constructible number is bigger than Q but strictly smaller than R. How will I show that? I will show that root 2 is constructible. How? This is my picture. So given, let's say you are given A, I want to form root A. How do I do that? First I draw A here, I draw 1 here. So this is a segment of A plus 1 length. You bisect the segment, get a center O. Once you get a center O, you draw a semicircle and then join this. At this point, draw perpendicular and join them. So now again you have two right angle triangle where this angle is equal to this angle is equal to this, and again you use the similar triangle idea. So you will get A by x equal to x by 1. That means x equal to root A. Thus you can form something which is not even a rational number. Yeah. The next thing I am going to discuss, what are the operations you can do using a straightedge and a compass. So these are the 4 operations. You can connect 2 given points through a straight line. Of course, you will do using straightedge. You can find the point of intersection of 2 straight lines. Third, you can draw a circle with given center and radius. And next, you can find a point of intersection of 2 circles or 1 straight line and 1 circle. These are the things you can do using your straightedge and compass. Okay, what is the method? So our process will go like this. First we fix a unit distance, as I said. Now we can construct Q by denoting that unit number 1. If we call that 1, we can construct Q. Let's say finally we will construct some number alpha n after n many steps. Alpha n is constructible, so it belongs to C. So let's say we constructed alpha I in the ith step. So this is a series of extension. I mean, first we construct 1, then alpha 1, alpha 2, and in nth step, let's say we construct alpha n. So this is a field extension. Here is the place where our theory plays a role in our problem. So till now, first we described the theory. What is a field? What is a field extension? After that, I described that using straightedge and compass, how you will construct some numbers, how you will construct Q. But now I will show the interdependence. So here you have Q, and let's say you have alpha. Alpha 1 you have constructed. So Q to Q of alpha 1 is a field extension. Similarly, Q of alpha 1 to Q of alpha 1 comma alpha 2, this is again a field extension. Thus, you will reach the final field Q of alpha 1 comma alpha 2 so until alpha. This is my setup. Till now I know this is a field extension. I don't know whether this has a degree or this is a algebraic extension. That will come later in the final part when I will discuss. And one more thing again you have to observe. You have seen the lemma, just that I have to apply it there. Let's say the degree of the extension Q of alpha 1 to alpha I minus 1 to Q of alpha 1 to alpha I is di. I mean, this degree is d1, this degree is d2. So until the final degree is dn, then the whole degree Q2 Q of alpha 1 to alpha n, this degree is nothing but the product of all them. In my lemma, I showed only for 2, but here you can just extend that by induction. So the whole degree will just be d1 multiplied by d2, so until dn. So these are my parts for these are my things for the second part. If you have any doubt, please ask me or unmute yourself or type. Otherwise, I will go to the final part. Does anyone have any doubt in this part? How this becomes a field extension? Okay, so it seems it is fine till now. So I will proceed and don't waste time. If you have any doubt, you can still type and unmute yourself. Yeah. So I already explained what are the 4 operations you can do using straightedge and a compass. So one operation was drawing a straight line, another operation was drawing a circle. So drawing exactly something, you can't associate algebra with that. But there are two more things. One is finding the point of intersection of two straight lines. Another one was finding the point of intersection of two circle or one circle, one straight line. That part has some algebra to be associated with. That I am going to explain now and find the relation. Let's say, okay, our setup is in plain paper, so it is R2. Let's say I have 0, I have the natural number and the rational number grid that we can also always form. But after that, what happens? Let's say the coordinate of some point is x0, y0. So if x0, y0 can be formed, that means x0 can be constructed and y0 can also be constructed. So now I am describing how do I find the point of intersection of two straight lines. Let's say the equation of one straight line is ax plus by plus c is 0. You know the equation of straight line looks like this, plus 2 coordinate geometry. Then let's say the equation of second straight line is a tilde x plus b tilde y plus c tilde is 0. So now you know how to solve this equation. You already a tilde, b tilde and c tilde. These things are belongs to f for some field f. Once all of them are belonging to f and you solve them, so x and y, you will always get a degree 1 equation. You will never get any equation of degree more than that. I mean, if you write x equal to something, that will always be a polynomial equation over x of degree exactly 1, just x equal to something. You can never go to any higher degree. That means the extension f to f of x and f to f of y, they are of degree 1. Okay, one caution here. I haven't worked out the equations and find out what exactly is the solution is, because everyone can do that. I just want to explain why this is a equation of degree 1 and this is very easy to understand. You can see. I hope there is no doubt. Now the next part is finding a point of intersection of one straight line and one circle. So again, the equation of the straight line, let's say x plus by plus c is 0. And the circle is x minus h whole square plus y minus k whole square equal to r square. But here you don't have a equation of degree 1. So what should be your strategy? You first find the value of x from the first equation, put that value in the second equation. So here you have an equation of degree 2. And once you have an equation of degree 2, this extension should be of degree 2. f2 fx and f2 f. Now comes the final part. So we have done for two straight line, we have done for one straight line and one circle. Now let's say point of intersection of two circles. So this is one equation and this is another equation. So here you have both 2 degree equation. How do you encounter them? You just subtract one equation from the another. Once you do that, you get a degree 1 equation because x square will be cancelled, y square will be cancelled. So now you have a degree 1 equation and one degree 2 equation. How do you handle them? Try to understand. Let's say this was your first circle, sigma 1, and sigma 2 is your second circle. So once you subtract one equation from the another, you get an equation of a straight line, as you can see in the previous slide. This equation, the new equation I found, is the equation of straight line. What is that straight line? That is precisely the straight line passing through both of the circles. So once you get the equation of this circle and this straight line and the circle sigma 1, finding these 2 points is nothing but finding the point of intersection between a circle and the straight line, which we already described. The degree must be 2. So the last, what I said is just written here. Is a point of intersection of one straight line and one circle. So again, the degree is of degree 2. Hence the extension f2 fx and f2 fy are of degree 2. Now this is the magical thing, not magical thing. This is the thing we need to understand to finally give answer to the questions asked in the beginning of the talk. I am saying if an element alpha belongs to R is obtained from a field F by a finite series of compass and straightedge construction, then the degree of the whole extension should be 2 power k for some non-negative integer k. Any alpha, let's say, you can construct. Then you can always think about the field extension f to f alpha. I am saying the degree must be 2 power k. Why? Okay, so this is not necessarily an exercise to the audience. I already described it. I will recall it once. I already said, let's say you have described, you have construct alpha 1, alpha 2, so until alpha n. So what about the whole degree? The whole degree is just the multiplication of degrees in every individual step. So previously we have showed that degree is always 1 or 2. In case of two straight line, it is 1. In case of straight line circle, it is 2. In case of two circle, it is 2. So in every individual step, let's say alpha 1 to alpha n, you are either multiplying it by 2 or multiplying it by 1. So finally, what will be your result? Your result must be 2 power something. It cannot be anything else. I hope this proof is clear. Yeah, so now I have reached the final theorem. It will take 5 to 10 more minutes. Before that, if you have any doubts so far, you can ask me. Whether you have asked the 2 power k thing, why this is true, please ask me by typing or unmuting yourself. Otherwise, I will state and prove the final statement.
Can you go back once more? I want to see the last page once.
Is this?
Yeah, I just want to read this once more.
Okay. So here I am basically using the proposition I wrote in the last step, that degree should be d1 into d2 so until dn. And in this part
Okay.
I saw, yeah, hello.
Yeah, okay.
Okay. Anyone else? Okay, so now I have reached the final theorem, and so far I told that the questions were asked how to trisect an angle, double a cube, and square a circle using straightedge and compass. And now you may be disappointed, but now we are going to disprove that these are possible. So basically, we are going to prove that using a straightedge and a compass, you cannot do anything of them. Greeks asked the question long back, but then people like Galois and all came. They developed algebraic objects like group, rings, fields, etc. They used the field extension and proved that these problems are not solvable using straightedge and compass. Finally, we are going to prove this. So, what is the statement of the theorem? That none of the classical Greek problems are solvable. So, there are three problems. I'll start with the first one. And I think some of you have already understood the proof because I think Suraj asked me in the beginning. So, doubling the cube needs to construct cube root of 2. Why so? Let's say you have a unit cube. So, whatever the cube given to you in this process, I will defining that side length to be my 1. So let's say I have a cube of I have a cube of volume 1. Now I need to construct a cube of volume 2. So if the volume is 2, what should be the side length? Of course, cube root of 2. So once I have 1, I have the whole Q with me. Q as in set of rationals. I can construct that field. And also I have to construct cube root of 2. So what will be the degree of that extension? The degree of cube root of 2 from Q is exactly 3. Why? Because I already showed in the example, the polynomial is x cube minus 2. So this degree is clearly 3. But what was my last lemma? Last lemma was that any extensions must have degree 2 power k. And as you know, 3 can never be equal to 2 power k for any integer k. So this problem is unsolvable. I am done with the first part. Now we will go to the second part. I hope no one has doubt with the first part. Okay. So the second part. Here I am proving that trisecting an angle is impossible. So the question was asked like this: given any angle, whether you can trisect it using straightedge and compass. The question was for any angle. So to disprove it, it is sufficient to give one counter example. If I can show that, let's say for this theta, I cannot trisect the theta, then I am done. The problem is unsolvable because this particular theta cannot be trisected. So what is that theta I choose? I choose theta equal to 60 degree. And then I am showing that we can never construct 20 degree, which is exactly theta by 3, using straightedge and compass. And why so? Okay, so for showing this, I need some more tools. I am claiming that if theta is constructible, theta as an angle, then cos theta is also constructible. How? Here is the picture. Let's say I can construct the angle theta. Once I can construct the angle theta, I can construct one here, and from this I can draw a perpendicular. So I can always form a right angle triangle with its hypotenuse 1 because I know what 1 is, and this angle theta because I know what theta is. So now, if you know basic trigonometry, what is the value of x by 1? This is exactly cos theta. So your x is cos theta. So this particular part shows that if I can construct theta, that is same as constructing cos theta. So if I can construct 20 degree, I can construct cos 20 degree. And now I am going to prove that constructing cos 20 degree is impossible. Then I will be done because constructing 20 will also be impossible. Yeah, now we show that cos 20 degree is non-constructible. How? This is one formula again from your plus 2. You can work it out. Cos theta equal to 4 cos cube theta by 3 minus 3 cos theta by 3. So you just put the value theta equal to 60 degree. So cos theta will be half. Yeah, let cos 20 degree equal to alpha. So if you put cos 20 degree equal to alpha, so you get a equation 8 alpha cube minus 6 alpha minus 1 is 0. How do you get it? So here you get cos cube alpha, here you get cos alpha, and in cos theta you get half. So you multiply it both sides by 2 and take that one to this side. So this is the equation satisfied by alpha. And this is a simple 3-degree equation. One can ask the question that why this is the minimal polynomial satisfied by alpha. There can be some 1-degree or 2-degree polynomial. So that is also left as an exercise. You can just prove that you cannot factor this in Q of x. 8 alpha cube minus 6 alpha minus 1 cannot be factored into different polynomials. So the degree is again 3. This is the minimal polynomial for alpha, and the degree is again 3. And again you know that the degree must be 2 power k. So degree can never be 3. The proof of the first problem was simple, but this has quite a lot of things. So if you have any doubt, please ask me. I will explain again because I have time. So how I started with taking the counter example 60 degree. I wanted to show 20 degree is non-constructible. For that I wanted to show cos 20 degree is non-constructible. I found the equation. I know the value of cos 60. Put it here. Get the equation, polynomial equation of alpha. This is a degree 3 equation. So the extension degree is 3, which is not 2 power k. That means it is also impossible. Now the final thing, whether it is possible to square a circle. Given a circle, whether you can construct the square of the same area. Okay, so now I am claiming that squaring a circle is equivalent to construct pi. Why? Okay, first you have to understand, given a circle, how do I find its center? So let's say this is the circle given to me. Nothing was there before and just the circle. What I do, I draw any, what is this called? Chord. Yeah, I do any chord AB. Once I do any chord AB, I can do it using a straight edge. I can bisect it using compass. Once I bisect it using compass, I will get this DE. And this DE will exactly be the diameter. Now I have the diameter of the circle. Again, using the compass, I can bisect it and I can find the center. So once given a circle, I have found the center using straightedge and compass. Now I can also measure the radius using compass. So let's say that radius I call 1. So if that radius is 1, what should be the area of this? The area should be pi. Once the area is pi, the area of the square should also be pi. That means I have to basically construct root pi as a side length of the square. So constructing root pi is same as constructing pi, because I have already showed if you can construct a, you can construct root a. So all I have to show that pi is not constructible. And again, this is a huge number theoretic statement I am going to use in the next slide without proof. That is that pi is not even algebraic. While giving an example, I told it, but now I am making it as a valid statement. But I am not making an effort to prove this, because proving this can also take another talk. So I am just claiming pi is not an algebraic number. That means if you are going to construct this q of pi, this field, this degree will be infinite. You cannot construct pi using finitely many steps. So this is the fact I am using, that pi is transcendental. So this extension is not even algebraic. And if it is not even algebraic, it can never be 2 power k. It should be infinite. And that's all. I mean, I can disprove all of them. So I am done with everything. If you have any doubt, please ask me. Or
Are there other problems like degree 5 problems which like so we solved a few for degree 3 and then we solved
yeah,
one for
there
degree
are quite a
infinite.
lot of problems. I will tell you. So the first one, let's say, can you construct a regular 9 gon using straightedge and compass? That you can see whether you can construct. There is another problem whether you can construct the angle 3 degree. I mean, the way I showed for 20 degree, you can ask the question for 3 degree, whether you can form the angle 3 degree. I think that degree will be something more, not 3. That will be 5 or something like 5 or 6. I don't remember exactly. Yeah. So these are the two problems. I can find more example maybe. You can. Yeah, yeah. These are the examples.
So what I didn't understand was,
Yeah,
are angles also considered to be constructible numbers?
yeah.
Like, are they a separate entity, or are they considered to be constructible numbers?
No, angles are not considered to be constructible numbers. I am saying if you can trisect the angle 60 degree, then you can construct the angle 20 degree. This construct has nothing to. Okay, so I think here I have used a bad notation. I shouldn't use theta belongs to C. I should have said that if the angle theta is constructible, then cos theta belongs to C. Angle theta doesn't belongs to C doesn't make sense. I have to say that theta can be produced or something like that using straightedge and compass if cos theta belongs to C. Because cos theta is a length, it can be constructed. Yeah, you have pointed out a right thing. Thanks. So theta belongs to C doesn't make sense. I can say that theta is producible if cos theta belongs to C. The lengths are constructible, not the angles. In
Okay.
our theta, the lengths are constructible. Yeah. Sorry about that. Thanks. Yeah, if anyone has any more doubt regarding the theory or regarding the proof of the final thing, or if you want to know, yeah, one thing I have to mention, if you want to know the proofs or the more theoretical things about this field extension or the lemmas, I left the proofs. So you can find it in abstract algebra by Damit Fute. So they have this field theory chapter. In that chapter, I think this is just like a chapter 14.3 13.3, chapter 13.3. You can find all the proofs, or maybe 13.2, abstract algebra by Damit Fute. That is the reference. That's all I had to say.